Hi IB Physics students. For this video, we want to talk about C 1.7, the magnifier on your textbook, page 14 and 15. I'll ask you to read these two pages first and I'll explain more in details. Before we start, I'll tell you what to pay attention to. First of all, let's have a quick recap on what we have learned before this in school. So we have learned about the thin lens formula to deal with the convex lens, concave lens situation. We also talk about very briefly about something called the power equation. Nothing to do with energy, but the power of the lens, something to do with the focal length. Also, we talk about the magnification related to the height of the ratio of the height of the image and object, or the image or object distance as well, and when to use positive or negative for these values. If you try to look at the data booklet here, you see that the next two items is also M, but they are capitalized M. So the difference between the small m and the big M are basically the small m is referring to the linear magnification, while these two big M, actually there are another one here as well. And all these are referring to the angular magnification. And notice that they are not the same. You can never assume they are the same. There are times or situations that they, in terms of number, they are exactly the same, but there are also times where they are not the same. So in fact, you can never assume they are the same. That would be, I would say, the best way to do. Okay, so in this session, mainly the ultimate goal is to understand how to use these two equations. Okay, for this one, this is by definition. Okay, it's being defined, and then we use this to derive this equation and this equation. You can see the word near point and infinity, which you understand more after you finish this video. Okay, so let me tell you what to read and pay attention to in these two pages. First mission I want to give you is find out what it means by near point. Okay. Second thing I want you to figure out is basically that two equations. So the first equation, and if you refer back to your data booklet, this is the equation actually for the infinity, that one. Yeah, so not this one, okay, but the one on the right hand side first. I don't know why the textbook make that, but anyway, okay, so maybe this one is easier. So you may want to remark on your book that this is for infinity. Okay, and infinity means the image format infinity. The next page, you also find there's an equation that you could derive. This is for the near point. Okay, image forming at the near point. However, when you try to read this and understand the whole thing here, there on this page there is a typo. Okay, so I want you to find it out, and through that I think you can understand better if you know how to derive the equation here. You understand what it means by near point or infinity in this case. Okay, so I'll give you some time. You may want to pause the video now and continue to video when you're ready. Okay, so first of all, what is near point? You can actually read, well, basically all these here. There's a word called straining, and if you don't know what this word, you can try to Google it, and basically it will tell you putting effort. So that means when we say near point in IB physics, it's talking about a distance for a normal eye. I mean, in fact, you may read like being very like doubtful or confused that, hey, how come is what do you mean by normal eye, and why would it be 25 cm? When I first try to learn this, I also feel very confused as well. So I fully understand like if you feel the same right now. So basically, for different people, apparently we all have different eye. Not to mention some of you already wearing glasses, but here is more like a standard, I would say. We are trying to follow for most of the people. If they don't need any glasses, then 25 cm is the one that you may say the expert think this is the best distance for normal eyeball for us to see, and this is a distance that we don't need to put effort. I mean, you can try to, without glasses, you can try to read books very closely or very far distance from your eye. You will find out you can still see it. It's just that you what you need to do would then be stretching or contracting your muscles very hard. Then that wouldn't be the so-called the near point. Okay, so this is just an idea. So I would say you could just recall the definition here. So basically it's without effort. It's a distance that you can see the object, see the image without effort. And from IB physics is always 25 cm. Okay. The other thing that when I'm not going to read the whole thing for you, but then one thing that you should pay attention is we use this small angle approximation here. Tangent theta nearly equal to theta, and that's because of the situation here. We got the D, which is 25 cm, the distance from the image to your eye. And if this is the angle, then we can have such a relationship, and that would be useful for the equation later on. In order to understand the near point better, I borrow a picture from Cognitive, which I find actually is better than the one you could see in a textbook. The one in the textbook only shows you that the so-called near point is when your eye looking at the image, and this is a distance. There's no lens here, so you may think that, oh, is it just referring to the situation when there's no lens? Actually, it's not. All right, of course we need to talk about the lens in this chapter. So this picture gives you a better idea. So that is to say, no matter where the object is, actually it doesn't really matter. All right, when we say set something to normal adjustment or set something to near point, okay, or sometimes they call normal adjustment. You see this word later on, later in the other section. So whatever it means is nothing to do with where the object is. It's more about the final image. Okay, this final image, the distance between that to your eye. Even though you can see in between this there are lens, even two lens sometimes in this situation, in this picture. Sometimes one lens, or even if there's no lens like the one that they provide to you, it doesn't really matter. Okay, so at the end of the day, when we say near point, it's really the final image and your eye having the 25 cm distance apart from each other. Again, when you look at this picture, you may ask another question. Hey, Mr. Wong, you may see that this is where you start to measure 25 cm up to the image. Well, image, eye here. So what about the distance, right? You may ask, like, so what about this? Do we ignore this? The answer is yes. Basically, you can ignore your distance here. You just measure from the first lens that your eye puts on. So imagine, well, this is called eyepiece, right? So imagine the eye is really sticking very close to the lens that you can basically ignore the distance here. And that's why the near point, we only measure from the first lens. Okay, so if there are two lenses, then you are measuring the eyepiece to the image. If there's only one lens, then you just, again, you also measure like between that 25 cm. Okay, so the objective lens doesn't really matter a lot. This is the understanding and basic definition of near point. So now we have to firstly talk about the angular magnification basic definition first. Okay, we also may call it these thing, all right, basically, as I said, the first principle. So similar to when you learn differentiation, there is a first principle of differentiation as well. This is again the definition, right? You can't argue with it. What you have to understand is that the angular magnification is defined as these two theta theta prime over theta. So apparently the original one is at the bottom and the new one is at the top, like the linear magnification. You may also want to understand that that actually means the original means is unaided. That means if you have glasses, when you wear glasses, it is aided. When you don't wear glasses, then it will be unaided. Okay, so that will be the basic definition of the angular magnification. You have to understand that. There's a really nice picture from, again, Cognity, which you may want to take a look here, which is it's just simply common sense. You may find, let's say these are all the trees. All the trees in itself, the size is the same. Let's say this is 2 meters, and actually all the trees, if you go there and measure them, all of them are 2 meters. But how come you see the trees at the far from you, those trees at the back will be smaller? This is simply because of the perception itself, that you find the angle from, if you look at this picture, the angle of the light coming from the top and the bottom will form a smaller angle if they are further apart. Okay, you form a smaller circle angle, and if it is closer, then it will make a bigger angle. So that's why you feel that it's bigger, but actually it's the same size of the tree if you go and measure them. And this is the idea of angular magnification. And this is very important, especially when we talk about the planet, because we can never go to the planet and measure the size of the planet directly. So that's why we instead will talk about angular magnification. Okay, so we'll come back here and let's take a look of this equation. Eventually we want to understand how come for image forming at infinity with the convex lens. Okay, so be careful, this one is a convex lens we are talking about. We would have this equation to represent is angular magnification. So the first thing that you need to recall is for a convex lens, if you want the image forming at infinity, according to what you learn, you have to have the object placing at the focal length f over here, exactly at f. Then the image will be forming somewhere at the infinity, okay, all the way here. Then that simply is the diagram, and using that you can already derive the equation very directly, because previously we already talked about you have to use the idea of small angle approximation. So the unaided one is when you put that object at the near point. So that would be this one, theta, original theta equals to h, which is the object size, divided by d, which is the near point distance. So for the unaided one, once again, it will be better if you understand this is not equal, but it's approximation. Okay, so that's why at the end you'll find out here is also approximation as well. So this is not a perfect equivalent formula. For the theta prime, you'll find out strangely is h over u instead, because if you normally talk about the theta towards the aided one, that should be referring to the image, right? But the thing is, the image actually form at infinity, all right, and you wouldn't know the size of whatever image projected at the infinity anyway. So how can you find out? The way that you have to do is by looking at the similar triangle. So actually this one you may want to write down is done by similar triangle. That you look at it by taking look of this triangle, okay, where the object and this one and the object distance is actually the same triangle as what we have for the image forming at the infinity, because this is the same angle, right? They share the same angle. So that's why you may use this equation instead. And well, interestingly, you will just simply find that because of the convex lens property, this will be exactly the same distance as the focal length for the U, right? Because in order to get the image form at infinity, you have to put the object at f. So that's why you can use the equivalent equation that theta prime equal to h over u, and then just simply by substituting these two things into the first principle equation, then you can get the final answer. So this is how you could understand for image forming at infinity, this is the angular magnification. Okay, so if you were okay with the previous page, this should not be hard for you. So once again, the objective of this page is to understand how come for image forming at near point, you may want to put down image forming at D, okay, near point, you may recall near point, which is 25 cm. How come the angular magnification is this equation? Okay, so in fact, the whole textbook here already provides you a very nice diagram where if you think about that, the only way that you can get the image at 25 cm, of course, it has to be inverted as well. Okay, so then the object must be between the lens and also the f, because you are trying to magnify it. So that's the only case. So in that case, you will have the v, which is the image distance at here, which is equal to d, but since it's a virtual image, then it will be negative. So by applying the thin lens formula, you may have deduced that u equal to this. If you don't know how to do it, I can do it here quickly. You just have to rearrange it, and then you expand it, d times f plus d, and you just have to inverse the whole thing, and then you can get this. Okay, so this step is still correct, this step is still correct, this step is still correct. Okay, there's no typo so far. The typo is actually right here. Okay, if you try to look at the equation here. So like I said in the previous example, when we talk about image forming at infinity, or some people may call it far point, then the new angle could be found by again using similar triangle. So this is a new angle, and that will be the same angle here as well. So finding out this is the same as finding out this. So you may have used h over u again at using this similar triangle, and then by substituting u from this, then you find there is a variable f missing. So this is a typo. Okay, so only with this, then you can lead to the next part. Actually, if you look at this, they somehow appear, it appear again, the f appear again. Okay, so if you substitute this, and also this is the usual one like the previous part, when you have no lens and you just simply put the object at the near point D, and so this is how you get h over d as the theta. Okay, and at the end you'll be able to derive this one. Okay, I'm sure you can get through this by yourself. So I hope through this exercise you can understand how we define near point, and also how what are the assumptions we need to get to these two equations.